Let's move to the next presentation, which is titled The Pipe Routing Hybrid Approach based on A-star search and linear programming.
Hello, everybody. My name is Marvin Stanczak. I'm a French PhD student working with the National Office on Aerospace Studies and with Airbus Defence and Space at Toulouse in France. I'm going to present you a hybrid pipe routing approach based on A-star search and linear programming. In the space industry, and especially in the communication satellites, we use waveguides. A waveguide is a pipe with a rectangular section which carries an electromagnetic signal between two components of the satellite payload. The roots of these waveguides inside the payload are often built as successions of straight sections and bands taken from a catalog. The designers use their knowledge to avoid obstacles and to save lengths and bands as much as possible. However, it is a highly time-consuming phase, and this is why we need automated procedure to route these waveguides. Waveguide routing is similar to pipe routing with additional constraints. There is a rich literature about the pipe routing, but mainly for pipe with a circular section. The most common approach uses graphs built by splitting the available space into regular cells or by using rules inspired by the designers to build a graph of candidate routes. And then they use a shortest path algorithm to route the waveguide, to route the pipes. So, more recent works have proposed a parametrical model for pipes before using mathematical programming to solve the routing problem. However, none of these techniques is reusable for the waveguide routing problem because none of them is able to deal at the same time the rectangular section of waveguide and non-orthogonal band taken from a catalog. Now I'm going to present you the waveguide routing problem that we consider. First of all, the straight sections and the bands as seen has functioned on the space of the configuration. A configuration is a position and an orientation of the pipe section. But straight section translates the configuration along the z-axis of the orientation with a given length. And for the band, three transformations are applied. The first translation with a given length, a rotation, and then the same rotation, the same translation than the first one. So a pipe can be described as an origin configuration and a composition of which alternates straight sections and bends. As a result of this definition, the trajectory of the barycenter of the pipe section all along the pipe, called neutral fiber, describes a polyline. For each segment of this polyline, we have a given length and a fixed orientation. About the routing space, communication satellites are often made of several panels on which the waveguide and the obstacle must be fixed. So the routing space is naturally divided into several cells. We assume that these cells are convex and do not overlap obstacles. However, we call interface the common part of two overlapping cells. This way, the pipe routing problem can consist in finding a pipe which start from the origin configuration and which end at the destination configuration. But we want to minimize the total cost of the pipe, which is defined by the sum of a first contribution, which depends linearly on the length of the pipe, plus a second contribution, which depends on the unit cost of each used band. Furthermore, we want that the waveguide or the pipe satisfies additional constraints, such as it should use a maximum number of bands taken from a given catalog. The neutral fiber of the pipe should be inside the routing space. Each straight section should satisfy a minimum length. And last, in order to ensure that the waveguide can be fixed on the panel it is routed on, we constrain the orientation of each segment depending on the cells that it crosses. To solve this problem, we propose to build iteratively the neutral fiber of the pipe. To do so, we introduce the notion of routing plan. A routing plan is an abstract description of the neutral fiber, which defines the used bands and the sequence of interfaces crossed by each segment. Moreover, a routing plan is said to be terminated if the neutral fiber has to reach the destination. From a plan, it is possible to deduce the orientation of each segment and the cell in which each vertex of the polyline is allocated. A routing plan is feasible if it is possible to build a neutral fiber that satisfies all the constraints of the plan. This, the feasibility of a routing plan S can be formulated as a linear program with the following variables: the length of each segment, the position of each vertex, the position of each intersection between each segment and each interface to cross, and the distance between the previous vertex and each intersections for the segment. The linear program minimizes the total cost of the pipe, depending on the length, and then we constrain the position of the vertices with the origin, with the allocated cells, and if the plan is terminated, with the destination. Then the position of the vertices and of the intersection points are linked using the orientation of each segment and the distance and the length of the segment or the distance for each intersection. Of course, the position of each intersection is constrained by the interface to cross. From a feasible non-terminated plan, there is three kinds of possible decisions. We can extend the routing plan by applying a new band, by crossing an interface, or by terminating the plan. The resulting plan of each of these decisions can be easily formulated with the definition of a routing plan. So the successors of the plan are the feasible plan that satisfy all the constraints and that result from one of these decisions. This way, the pipe routing problem can be formulated as a shortest path problem in the space of the routing plans. The goal is to find a path between an empty plan starting from the origin and a feasible and terminated plan ending at the destination. To solve the problem, we propose to use the weighted R-star algorithm, which explores the more promising plans using an evaluation function. This evaluation function is the sum of the cost of the routing to reach the routing plan given by the linear program LPS, plus epsilon times a pathfinding heuristics, which estimates the distance to reach the destination from the current routing plane S. A first naive heuristics consists in using the as-crossflies distance between the last point of the neutral fiber, which is also given by the linear program, and the destination. It's a naive heuristic because it's completely doesn't take into account the topology of the routing space, but it is used as baseline. To improve this estimation, we introduced the notion of trail. A trail is just a polyline which connects the last point of the neutral fiber to the destination, but which stays inside the routing space. To build these trails, we sampled points on each interfaces of the routing space, and then we built a graph.
Sorry, just a reminder, 3 minutes left.
Okay.
It's just your 3 more minutes.
Okay. Excuse me. And then we built a graph by connecting the sample points on neighbor interface as well as the destination. And then we evaluate the distance of each sample point to the destination using a Dijkstra algorithm. So we can use the estimation as estimation the length of the shortest trail for our routing plan S. It could be improved, this estimation could be improved by using an extended routing plan by crossing as many interfaces as possible from the plan S along the shortest trail for the plan S. This time we use the cost difference between the extended plan plus between the extended plan and the original plan, plus the shortest trail of the extended plan. But we can also use the trail to estimate the band cost. To do so, we start from the last orientation of the plan, and we estimate the best band combination to follow the trail. And to estimate the band cost, we use the cost of the band combination plus the minimal, the cost of the minimal bands to reach a destination orientation from the resulting orientation of the combination. This approach has been tested on with the free heuristics on 4 routing instances inspired from the literature and with gradual complexity. The routable space of these instances contain from 8 to nearly 80 cells, and we use a band catalog with 45-degree and 90-degree bands. The experimentation has shown that, as expected, the as-crossflies distance allow to solve only instances with very few cells. And in the opposite, the trail length heuristics succeeds to solve larger instances with good solution, but only with a large value of epsilon. And the most complex instances stay unsolved. However, the trail cost heuristic, which estimates the distance plus the band cost, allows to solve all the instances and is really more robust. Moreover, this last heuristics provide really pretty good solution, as shown on this figure, that are completely acceptable for waveguide design. The resolution time for the most complex instances are is within about 2 minutes, which is reasonable and which is acceptable for the first industrial use. To conclude, we have proposed a pipe routing technique adapted to the waveguide routing problem. That means it deals with oriented section and non-orthogonal band taken from a catalog. And this approach has succeeded to solve industrial instances within a reasonable time and providing acceptable solution. As perspectives, we will try to improve the performances of the algorithm by warm starting the linear program using the solution from the previous routing plans. Of course, we will compare the approach with a full MILP model. And last but not least, we will try to use this approach to tackle the multiple pipe routing problem. I thank you for your attention. And I'm happy to answer questions.
So many thanks for the presentation. By the way, this was a very interesting problem. Are there questions from the room or from the people online? Peter?
I'm wondering why you needed to use weighted A stars, because your heuristics, you don't trust them. So essentially you're sort of giving up on the guidance from the heuristic.
Could you repeat your question, please?
You use weighted A star, which kind of makes it more Dijkstra-like than A star-like if the weight increases. Is this because the heuristics aren't that trustworthy? They're too low. They're too much underestimate.
It's just because the combinator risk is very high, and we want to have very quick solution, not the optimal one. So the epsilon in the weighted ASA aims to get a more aggressive algorithm. And it's just a first approach, a first shortest path algorithm approach. The idea behind is to test later more aggressive algorithm to get very quickly a solution, because the operation has to be very, the problem has to be solved very fast in practice in the industry.
Yeah, okay. So you're emphasizing the G cost over the H cost. Yeah. So there's an advantage, but to be further along the potential path, right?
Okay, also a quick question. And so since you have a feasibility problem that can be modeled as an LP, it seems like you could tackle your planning problem using an integer approach and then go for a bandless decomposition. You can generate cuts from the LP feasibility problems using an automatic procedure. Do you think it is possible? It may be interesting.
Yes, I think it's possible to generate cuts from LP and to add it in the search.
Okay, so if you want, just have a look at the bandless decomposition. If you are familiar, I don't know if you're familiar with that or not.
Yes.
Okay, well, I don't know. It may be something to try. Just this.
Okay. Thanks.
Okay, thanks again.